Welcome to my new calculus channel. My name is John Gabriel. As you might recall if you watched the previous video, part 12, I dealt with the myth of infinitesimal expansions and how they began, namely with Newton's ideas about infinite series. So in this video, I quickly want to just summarize what we covered then and continue with some very basic concepts in mathematics. So there are no infinitesimal expansions as we saw in the last video, and infinity is not a limit. So we can't really write something like this because infinity is not a number, okay? And when in mainstream mathematics, academics write this, it means that there is no limit, okay? So if they write limit of 1 over x is x approaches 0 is equal to this, there is no limit. Now, don't worry. I've actually jumped ahead here, but I'm going to go right back to the basics. So there is no such thing as an infinite limit. And then, of course, again, for those who are advanced in calculus, s is equal to lim s is the problem behind all of these ill-formed concepts. So, for example, if you have the standard normal distribution, this area beneath the curve is never equal to 1. Okay, it is bounded above by 1. And this here is called an improper integral because it's not really an integral in terms of the area per se. It's actually a limit of the areas, okay? And when we calculate z-tables and the scores that we see in those tables, we're actually using definite integration. So there's nothing about infinity there. So anyway, let's go back to the story of how we got mathematics. I don't want to spend too much time on that. So let me just clear this out here. New, don't save. Okay, so in book 1, the Greeks never actually defined area properly, in my opinion. And they only defined it after they defined number, which is pretty strange because they had defined multiplication, division, subtraction, and all the other arithmetic operations with magnitudes, even before they had number. So it seems strange that they hadn't defined area, volume, hypervolume, etc., until only after they defined number. Now, the definition of number is in book 7, and also the closest they came to defining area and volume was in terms of a plane and a solid. So they would say a plane is the product of the two sides of a rectangle, okay, or a rectangular figure. And likewise, a volume is the volume contained in a type of a cube, okay? So or a family of cubes. Now, the Greeks never actually had a word for arithmetic mean in the time of Euclid. And today, if you look at how the Greeks talk about an arithmetic mean, they'll say it's arithmetikos mesos oros. And they'll write it like this: mesos oros, okay? Oros. And that means middle term or middle. Oros can mean a lot of things. I mean, it can mean boundary, etc. And of course, mesos is very similar to the word misos, okay, which means half, right? This here just means the middle term. So they didn't really have a full understanding, or if they did, then they didn't actually express it correctly, because an arithmetic mean, they rejected infinity. So an arithmetic mean is really that value which would represent all the elements in a given set or in a given list if they were all made equal through redistribution. That is what is an arithmetic mean. And there is only one language that I've found which has a very beautiful word for arithmetic mean. It's Chinese. And the word, the pronunciation in Chinese is Pingjun. Okay, so Pingjun means level and equal. So An area is really just the arithmetic mean of all those vertical lines multiplied by the arithmetic mean of all the horizontal lines. And I'm talking about the length. So it turns out that if this is the height and the breadth, then the area is the height by the breadth. Now remember, in book 5, all the arithmetic operations are defined in, and in fact, not only the arithmetic operations, but the theory of fractions are all defined in one proposition, book 5 and proposition 12, which deals with similar triangles. It doesn't say anything about similar triangles, but that's where Euclid got those results, okay, about proportion, and from which all of our algebra and arithmetic comes from. So anyway, the Greeks never really understood that area is really the product of two arithmetic means, okay? H is the arithmetic mean of all the vertical lines, and B, the arithmetic mean of all the horizontal lines. And so that's how area is well defined in an abstract way, okay? The arithmetic mean of all horizontal lines times the arithmetic mean of all the vertical line lengths, by the way. Horizontal line lengths and vertical line lengths. All right. So, and similarly, a cube would be defined as, okay, would be defined as the product of three arithmetic means. This distance times this distance times that distance, and that would give you the volume. And of course, the Greeks called this a solid number, okay, a solid number, rather than calling it the product of three arithmetic means. And now, of course, formulating the first rigorous calculus for me involved actually finding a well-formed abstract definition. I mean, plane can be derived systematically, and so can solid, but without learning about the arithmetic mean, which is the second most important concept in mathematics, after number, that is, it's very hard to fully understand how calculus works. And nobody actually understood the mean value theorem before I came along. They would state some unremarkable result about it. It turns out the mean value theorem in calculus, which is the reason all calculus works, and it should be called the fundamental theorem, because indeed the fundamental theorem is derived in one step from it, is the reason that calculus works, and it is in actual fact an arithmetic mean. But I'm not going to go into that right now. So going back now to the book of elements and the first chapter, because I'm going to cover some of these concepts. Now, the Greeks would often use constructions, but those constructions are not actually needed, in fact, in the theory. And they're only used as reifications, okay? So that means they would use those concepts, those constructions, to talk about the perfect ideas, right? They would use, let's see, let me just get a pen there. Okay, they would use, like, say, for example, you want to construct a right angle, you draw a straight line and then put 2 points there, and then take your compass and just go more than halfway, and then do a marking like that, and the same from this side. And then, of course, you join these 2 points, this point and this point, and you've actually created a perpendicular line. Or alternatively, you could just take your compass and straight edge and draw a circle like that, and then again mark it out from this side, and then join this point and this point, okay? So something like that, okay? The constructions are not important. They're just a matter of speaking. When we talk about a point, we mean the concept. In other words, where is it? The location, okay? So these here are not points. They're just reifications of point, and they're not perfect constructions. Only much later, with the advent of René Descartes, were we able to reify a point in terms of number, okay? The Greeks used conic sections to do they had a conic coordinate system. All right, it wasn't the same as Descartes. So you can reify anything using the cone, and you can learn how to do that in my book on calculus. But right now, that's all I wanted to show you in this particular video, is that you should think of constructions as a means of communicating these concepts, right? Constructions are not needed in the elements. So you can talk about a line, and when you talk about a line and you draw a line as you would normally like this, you're talking about this distance here between these 2 points, okay? And a straight line would be the shortest distance, that one. And similarly, a circle, you're talking about the distance of the circumference, and a triangle is the shortest distance when joining these 3 points, okay? So that's not really a triangle, it's just a visualization or an instantiation of the triangle. So I wanted to get this concept clear, because in the following videos I'm going to talk about these basic concepts and continue to show you how we can derive and understand mathematics using only well-formed concepts from a void universe. So if you haven't done so already, I'd encourage you to go to part 1 of the series and watch all the previous videos so that you can understand what I'm talking about, because I'm not actually going to go back to those concepts. So I'm going to deal with them one at a time, and in future I'm going to try and produce short videos, hopefully not longer than 5 minutes, and I'll hopefully cover all these concepts, and we'll work our way right up to calculus that you've learned, if you have learned it, or if you haven't learned it, using only well-formed concepts. No infinity, no limits, no infinitesimals, no set theory, no real analysis, no other nonsense. Okay, so I hope you've enjoyed this little presentation, and this is a new calculus channel. My name is John Gabriel. Till next time, goodbye.